some nitrogen derivatives of carbonyl compounds. That pen's no good. I pointed out that you can convert carbonyl compounds into a number of derivatives that have nitrogen in them. This was one of the types of derivative. Another type was this, which is called an oxime. This is an imine. And the final type hydrazone, and I probably pointed out that a certain type of hydrazone called a 2,4-dinitrophenyl hydrazone is often used, has often been used to characterize carbonyl compounds. Now, what do I mean by all that? I'm not going to go over the mechanism again, but I did point out that these things are acid catalyzed. What happens is that the carbonyl is protonated, and then the nitrogen of the, in this case, of the amine, that lone pair attacks the carbonyl, and here the nitrogen of the reagent, which is hydroxylamine, attacks the protonated carbonyl, and here the nitrogen of hydrazine attacks the protonated carbonyl. And I probably then said that a certain type of hydrazone, a 2,4-dinitrophenyl hydrazone, has been used to characterize carbonyl compounds. What I mean by that is that the 2,4-dinitrophenyl hydrazones are very often crystalline compounds, and they have characteristic melting points. So if you have a substance that you think is an aldehyde or a ketone, you can make the 2,4-dinitrophenyl hydrazone. They're highly colored and frequently sharp melting crystalline compounds, and so you can measure the melting point. And there are tables of melting points of 2,4-dinitrophenyl hydrazones of very many simple aldehydes and ketones, and if your melting point matches one of the melting points given in the literature, then you are justified in suspecting that the aldehyde or ketone whose derivative you've made is indeed the one that gives a 2,4-DNP with the indicated melting point. It's not foolproof, so what you do is you make another derivative such as an oxime. And those are also frequently crystalline. At least that's what books say. When I was an undergraduate, I never could get a nicely crystalline oxime. I don't know why. Hopefully if I tried it again now, I would be able to do that. But I'm not going to try it because these days there are other ways. There are spectroscopic methods of finding out what aldehyde and ketone you have. So that's how I ended up the last lecture. And what I want to do now is to give you another example of addition of a certain reagent to the carbonyl carbon of an aldehyde or a ketone. And the reagent that I'm going to tell you about is cyanide ion. If you take a ketone, for example, or an aldehyde, and treat it with cyanide ion, together with some acid, then what what you will get is a compound like this called a cyanohydrin. That's the name of this type of compound. On the same carbon, it carries a cyanide group, C triple bond N, and also a hydroxyl group. Now, I need to tell you how this is formed, and then what I need to do is to tell you why this is an important reaction. Now, the way that it's formed is it works for aldehydes and ketones. I'm just going to use a generic structure like this. The cyanide ion, which has the structure that I've written, attacks the carbonyl carbon. And of course, it's very normal for nucleophiles to attack a carbonyl carbon at the carbon, because the C double bond O is polarized in such a way as to put a build-up of electron density on the oxygen and a deficit of electron density on the carbon. So anything that's got electrons will attack the place that wants electrons, that's deficient in electrons. Some of you have asked me what I mean when I sometimes write this and sometimes I'd write that. It's exactly the same thing. It depends just how I feel. It means it's an equilibrium. The reaction is reversible. Now, if there is a little bit of HCN in there, that process takes place and you get the cyanohydrin. So the way you do this is to add potassium cyanide to a solution of your compound in the presence of an acid. There are other ways of doing it. When I was a postdoctoral fellow at Harvard, I had to use some liquid hydrogen cyanide, which is quite a dangerous substance. And so what you do is you put on your NACO cylinder, you have a face mask that you're breathing in air, and you tell your friends in the lab that if you fall over, they should drag you out, and you give them some ampules of amyl nitrite. And if you did have an accident, they would crack open one of these ampules and hold it under your nose, and that would restart your breathing and your heart and so on. So I was wearing this stuff. This was late at night, and I never put on before, one of these big masks with the tubes on the tank and so on. So I was pretending to be a fighter pilot. And I was giving a running commentary to my lab mate. And guess what happened? My supervisor, Nobel Prize winner, walks in. And he walks in and makes a comment, I guess I've come at the wrong time, to turn around and walk out. I always wanted to be a fighter pilot. It's the speed that would attract me. Okay, so this is a cyanohydrin. Now, why is the making of cyanohydrins important? Well, the reason why it's important is that these things can be converted into a number of other compounds. In particular, two of them are very, very important. One is that if you take this substance and you boil it up with acid, what happens is that the nitrile group is converted into a carboxyl group. So what's happened in this transformation is that this piece has been converted into a carboxyl group. So this is a way of making carboxylic acids. Now later on, I'm not going to do it today, but later on I will write the mechanism of what's going on. It's a process called hydrolysis. Let me write that down. Hydrolysis. And you can see that the oxidation level of the carbon here is the same as here. This carbon is attached by 3 bonds to an electronegative atom. So it's the same as being attached by 3 bonds to 3 electronegative atoms. This carbon is attached to 1 electronegative atom and to another one by a double bond, so it's the same as being attached in total to 3 electronegative atoms. And so the oxidation level is the same. Going from the nitrile to the acid is not a reduction, it's not an oxidation, it's something called a hydrolysis. So this is a way of making carboxylic acids, which will be the next functional group that we're going to talk about. So that's one important reaction of nitriles. The other important reaction is if you take a nitrile, well, let me write it again over here for you. If you take cyanohydrin, I mean, let's write the whole line for you. And you treat it with lithium aluminum hydride, then what happens is you get an amine. An amine, remember, is simply it sounded like a cell phone. The first cell phone I had played appropriately God Save the Queen. The second cell phone I have got is a much cheaper one. It won't allow you to change the written tone. I have to do with this rubbishy pop music garbage that they're programmed into it. An amine is just a derivative of ammonia in which either 1 hydrogen or 2 hydrogens or all 3 hydrogens have been replaced by carbon pieces. Could be methyl, ethyl, propyl, cyclohexyl, phenyl, or any combination of these things. So this thing is clearly an amine. And the way that it works, you can probably work out for yourself how this happens, because you know from a previous lecture that lithium aluminum hydride behaves like a source of hydride ions. And just as with a carbonyl group, in which the double bond is polarized so that there's a buildup of negative charge on the oxygen and a deficit of electronic charge on the carbon, the same thing happens here. This bond is polarized. So a hydride ion, which got electron density, will attack the carbon rather than the nitrogen. So if it does that, what you get is this, and this is clearly affiliated with some metal, either aluminum or, so we'll just write metal or lithium, and then another hydride comes in. And then when you pour that into slightly acidic water, you get the amine. So this is exactly analogous to what happens if you treat a carbonyl compound with a hydride source. And remember, for carbonyl compounds, ketones and aldehydes, you can use sodium borohydride or you can use lithium aluminum borohydride. And for esters, you use lithium aluminum, sorry, not lithium aluminum borohydride, lithium aluminum hydride. and for esters you must use lithium aluminum hydride. So this is exactly the same, except there's nitrogen there, but the principle is the same. And so the formation of hydroxyamines via cyanohydrins is one of the important reactions of cyanohydrins. Now supposing, just supposing, that you wanted this substance, how could you make it? Well, one of the things that you could do in analyzing how you might approach this is to say, well, I know at least one way of making a carboxylic acid. In fact, you should know at least two. Oxidation of a primary alcohol to an aldehyde, and then further oxidation to the acid. But I've just shown you one in which this comes from a nitrile group. And so you know that if you can make that cyanohydrin, then you could make that acid. And how do you make the cyanohydrin? Well, you make it from the ketone and cyanide ion. And this so you can work backwards from that target molecule and devise a synthetic route. This is what medicinal chemists do all the time. If you go into the pharmacy to buy some medicine, somebody has worked out how to make it. They've looked at the structure that they want, and then they've worked backwards until they come to starting materials that are cheap, readily accessible, and then somebody else has made this, the compound. So people, professional chemists, do this all the time. What you are mostly doing is learning in the forward direction. If you take so-and-so, treat with such and such is what you get. That's the easy part. You probably think it's terribly difficult because there's a lot of it. But the hard part is to look at a target and work out exactly how to make it. And if the target is really complicated, there are millions, literally millions, of possible ways of making it. And you have to work out a good way. Supposing that you would like this compound. Again, there must be quite a number of ways in which this could be made, but based on what I told you today, you will recognize that one of the possibilities is to take this nitrile and reduce it with lithium aluminum hydride. And that cyanohydrin would come from cyclohexanone and cyanide ion. Now I want to give you a slightly more complicated example. Supposing that is the problem. The question is, how can you do this? Well, what you do is you work backwards. You say to yourself, one of the possibilities is that I take that cyanohydrin and treat it with lithium aluminum hydride. Once you've done that, you ask yourself, how can I make that cyanohydrin? Well, you know how to make cyanohydrins. You make them from aldehydes. And so what you really would like is that aldehyde. But your boss has told you you've got to start with that alcohol. And so if you oxidize the alcohol, say with PCC, you'll get the aldehyde. If you convert the aldehyde to the cyanohydrin, you can then do a lithium aluminum hydride reduction and get the amino alcohol that you want. So it's all very, very logical. And the way that it's done is to look at the product and ask yourself a few questions. Is there any feature of the product that I know how to make? Well, if you look at that product, it's an amino alcohol. And I've just been telling you how to make amino alcohols. And so you work backwards, and you then arrive at that type of approach. Now, what you should do is problem 16.6, which is also 16.6 in the 9th edition. 16.16. It's 16.16 in both editions. Now I come to the final reaction of carbonyl compounds. I've been telling you about formation of cyanohydrins. At the end of the last lecture, I told you about the formation of imines, oxenes, and hydrozones. Now I want to tell you about something called the Wittig reaction.
Well, it's not a new class. We don't have one right.
This is a final. I would have got with the crowd.
Having fun. Mm-hmm. Oh my.
So this reaction, the Wittig reaction, for which Dr. Wittig got the Nobel Prize, he shared the Nobel Prize with somebody called H.C. Brown, Herbert Brown, and Herbert Brown got the Nobel Prize for the hydrochloration work that I talked about, mainly for that. Wittig got the Nobel Prize for discovering this reaction. And you can see that it is a method of converting a carbonyl compound, such as an aldehyde or ketone, aldehyde or ketone, into a double bond. And the thing to notice is that one end of the double bond is the carbonyl carbon of the aldehyde or ketone. So that means if you take an aldehyde or ketone and use the Wittig reaction to convert it into an olefin or an alkene, you know for certain where that double bond is. If you try to make a double bond, say by dehydration of an alcohol, sometimes you can't be certain where the double bond will be because dehydration might occur on one side of the alcohol or on the other side. But with the Wittig reaction, that doubt disappears. You know absolutely where the double bond is going to be. So what I have to tell you is, how does all this work? Now this is a ketone or aldehyde, that's no problem for you. This is something you've not seen before. This is something called an imide. An imide is something that has opposite charges on adjacent atoms. You can see that on phosphorus there's a plus, and on the carbon there's a minus, and they are adjacent atoms. So that's an imide. You could write another resonance structure, but we won't worry about that. So the first thing, and this is an olefin obviously, so that presents no problem to you. The ketone and aldehyde presents no problem, but that phosphorus thing is a bit strange. So you need to know how to make it, and you also need to know how this phosphorus piece, this so-called imide, reacts with the carbonyl compound to generate a double bond. Well, the first thing to tell you is how to make the imide. If you take triphenylphosphine, that's just phosphorus with 3 benzene rings on it. And that shouldn't present to you any sort of problems, you know, what sort of strange beast is this? You shouldn't be thinking along those lines, because you know, for example, the substance called ammonia, there's a related substance called phosphine, and you know for ammonia you could have 3 alkyl groups or 3 aromatic groups, and exactly the same way for phosphorus you can have 3 aromatic groups. So this triphenylphosphine is a white crystalline solid. It's just got 3 phenyl groups attached to phosphorus. Now what you do is you take an alkyl halide. Let's take the very simplest one. Let's take methyl iodide. And you heat these two together. And what happens is you get an SN2 displacement. And you get that iodide, which is a crystalline compound. Now if you treat that iodide with a strong base, and one of the bases that's very frequently used is butyl lithium. Now butyl lithium is something that you can buy, but it is very easy to make. All you do is you take butyl iodide or butyl bromide and you treat it with lithium. And if you do that, you will get butyl lithium. It's exactly the same as making it, it's exactly analogous to making a Grignard reagent. If you took butyl bromide and magnesium in ether, you know you would get butyl magnesium bromide. Well, if you take butyl bromide in THF or in ether and treat it with lithium metal, you will get butyl lithium. Now butyl lithium is a strong base, and what it does, I'm going to write this a little differently. I'm going to put the 3 hydrogens like this. What the butyl lithium does is it deprotonates that salt. So now I have the imide from triphenylphosphine and methyl iodide. So now you know how to make these imides. What you do is you take triphenylphosphine and you heat it in an inert solvent with an alkyl halide, which is a primary halide or a secondary halide. You don't do it with the tertiary halide because SN2 reactions don't work with tertiary compounds. At least not SN2s don't work. So and also you need a hydrogen on this carbon. So you can make an ylide. This is the simplest one. Now I want to show you how the ylide reacts with the carbonyl compound. Why don't I take a very simple carbonyl compound? Let's take this one. And I'm going to treat it with the ylide that we've just made. Now, the mechanism of the Wittig reaction, if the truth be known, is in fact very complicated. But the mechanism that I'll give you is a simplified version, and it's good enough for all professional chemists because it gives you the right answer. And it's not too far from the truth as we currently understand it. Look what I'm going to do. So I've made a four-membered ring. Now, to your eyes, this is a strange four-membered ring because the only four-membered rings you've seen so far is cyclobutane. But this four-membered ring has so-called heteroatoms in it, in other words, atoms that aren't carbon. But that doesn't matter. And now, I'm going to allow it to break up into two components, one of which is the olefin, the alkene. The other one is triphenyl phosphine oxide. Triphenyl phosphine oxide, which is a white solid. So you can see where one of the carbons of the double bond comes from. It comes from the ylide. This reaction was discovered by Wittig by accident. He was doing something, he got out a product, it wasn't what he wanted, he worked out what it was an olefin, and he said to himself, my God, if this is general, I'm going to be famous. And he was right, because he examined the whole business further, and he certainly did become famous. So, you know in a very simple example how to use what's called a Wittig reaction to make a double bond. Now the expression Wittig reaction generally implies the whole business of making the phosphorus salt, generating the ylide, and then allowing the ylide to react with the aldehyde or the ketone. So just to make sure that you understand it, that you understand this business, because it is a very important reaction. You don't get the Nobel Prize for inventing the Mickey Mouse reaction. This is not a Mickey Mouse reaction. I'm going to work through for you a much more complicated example. Supposing you want that compound. Now that compound you recognize is an olefin or alkene, and one of the things that you could say to yourself based just on what you're supposed to know, that is to say, Chem 261 and what I've taught so far, one of the things you could say to yourself, well, the most conspicuous feature of this thing is the carbon-carbon double bond in the side chain. It's an alkene. Do I know any ways of making alkenes? And the answer will be yes. And then perhaps the next thing you could ask yourself, what's a really cool way of making alkenes? And probably, hopefully, the answer to that would be by Wittig reaction. Now, if you're going to make this by a Wittig reaction, you need to realize that you need two components. You need the phosphorus-containing imide, and you need a carbonyl compound, and one end of the double bond will come from the carbonyl carbon. So this double bond here has two ends. So two possible carbonyl carbons are available for you. If you use this one, you'll need a certain imide. If you use this as your carbonyl carbon, you'll need another imide. So let's do this one first. So if that's going to be my carbonyl piece, so this bit is going to be related to that part of the structure. So I need a phosphorus piece related to this part. And the imide that I need is clearly this one. Because if you follow through the reaction of that imide with the carbonyl compound, with acetone, you'll end up with a compound that you want. There are a couple of puzzled, frowning faces in the first few rows. If anybody doesn't follow that, for goodness sake, tell me now so that I can explain it again. So how do you make this imide? Well, you make it by deprotonating something. What do you deprotonate? What you deprotonate is a phosphorus salt. We'll say XA bromide. And how do you make that phosphorus salt? Well, you make that by carrying out a nucleophilic displacement on a suitable bromide with triphenyl phosphine. So what you do is you take that bromide that I've written right at the top of the board, and you heat it in an inert solvent like benzene or toluene with triphenyl phosphine. If you set that up late at night, say 11 o'clock before you go home, when you come back in the morning and cool down the mixture, you get a nice crop of crystals, which you can filter off and dry. And the crystals will be this bromide. And then you treat that bromide with butyl lithium. To deprotonate it, and then you react that with dry acetone. And if you do that, you will get the target compound. You guys are lucky because you can buy butyl lithium. When I was a student, I had to make it. Also had to make methyl lithium. It was a good way of finding out if methyl lithium was good, which I never used, but somebody in another lab at Imperial College did use. You sucked it up into a syringe and you squirted it across the room. And if it behaved like a flamethrower, you knew that this stuff was good. A very dangerous thing to do. But the fellow who did that was obviously a bit of a nutcase. Okay, so if this is going to be the carbonyl compound, this is going to be the imide. But let's do it the other way around. Supposing that it's benzaldehyde that's to say this compound, that's going to be the carbonyl compound. Well, if it's going to be the carbonyl compound, the imide that we want is this material. And that material will come from this phosphonium salt by treatment with butyl lithium. And that salt will come from isopropyl bromide plus triphenylphosphine by heat. And so if you have this illid and then treat it with benzaldehyde by the Wittig reaction, you will then get the compound that you want. So whenever you see a double bond compound that you want to make by means of a Wittig reaction, you have to consider the possibilities of using the left-hand side of the double bond as the carbonyl component and the right-hand component of the double bond as the phosphorus component, or the other way around. And which way you go for could depend on all sorts of things. It depend on which carbonyl compound you actually got in hand, in stock, and it can depend on some other things as well. Now, what you ought to do to make sure that you understand all of this stuff is the following. Which is also 16.19 in the 9th edition. 16.20 A through to L. 16.21. 16.22. It's all the same in the 9th edition. And 16.30 A to I, and that's equivalent to 16.24 in 9th edition. And lastly, you should do 16.38, which is equal to 16.32 in 9th edition. So those exercises will make sure that you understand the things that I've been talking about. Now, I need to change gears and go on to chapter 17, but before I do that, you remember that last week we decided that, not this week, but next week we would have that makeup lecture, and also I need to find a date for the big help session in which I'll cover everything that's on the final exam. So next week, which is the week of the 17th. Sorry? We did 21st? No. What's today? Oh, I'm looking the wrong month. Okay, today is the 14th. Next week, what evening at about 5 or 5:30 would you like a 50-minute lecture?
Can we do it on Wednesday, please?
Sorry?
Wednesday.
Okay, all right. Hang on a minute. Show of hands for Monday. Show of hands for Tuesday.
5:30.
Show of hands for Wednesday.
Ow.
Show of hands for Thursday. Right, Thursday. Show of hands for Friday. Show of hands for Saturday. Sunday. Okay, it's Thursday.
24th.
Thursday the 24th. 5 or 5:30?
5.
5:30. I'll find out what the room is. That's Thursday the 24th. Now you need to decide, and we won't decide it today, maybe we'll decide it this Friday. When would you like the big help session, which will be during the day, before the exam? That's when it will do most good. And after the end of the lectures. And I will cover the whole lot. It may take 2.5 hours. So you need to think about when you'd like that, because you all know when your other exams are, and you know when this exam is. All right, having said that, I need, in the last 5 minutes, to talk about carboxylic acids.
Or maybe like
Thursday night they're going festival tree. Saturday morning festival tree. A little bit down the birthday.
very busy.
So this is now chapter 17.
I don't want to start a new paper.
Arms minus for sure.
So carboxylic acids are compounds of this type. This is called a carboxyl group. And that carboxyl group can be on an aliphatic piece, methyl, ethyl,